Hi, my name is Jamie DeYoung and I created this video about power series representations of functions for MAT136 at the University of Toronto. So the purpose is to go through an example of finding the power series representation for a particular function and also determining when it converges, and then I'll leave you with an exercise at the end for some practice. So the particular series that we're going to the particular function that we're going to look at today is the natural log of 1 minus x cubed. So we'd like to find a power series representation for this. Now, we've looked at a lot of rational functions in class. This isn't rational, but it does differentiate to give a rational function. So we're going to have to differentiate it, then figure out the power series, and then integrate to get back to a power series for this function. So when we differentiate the natural logarithm, we get 1 over 1 minus x cubed, and then we multiply by the derivative of the 1 minus x cubed, which is negative 3x squared. We'd like to put this in the form 1 over 1 minus something. So we'll pull the negative 3x squared out in front, and what's left is 1 over 1 minus x cubed. So in this case, the x cubed is the thing we're subtracting, which means x cubed is what goes into our sum. So based on what we know about geometric series, this is the same as negative 3x squared times the sum from n equals 0 to infinity of x cubed to the power n. Now, we can tidy this up a little bit. We have x cubed to the power n, that's x to the power 3n. It's also multiplied by x squared, so that actually becomes a power of 3n plus 2. So we have negative 3 times the sum from n equals 0 to infinity of x to the power 3n plus 2. Now, this is a geometric series. It has a being negative 3x squared and r equals x cubed. And based on what we know of the geometric series test, that means it converges when the absolute value of x cubed is less than 1. Or in other words, when x is between negative 1 and 1. And we'll note that that means the radius of convergence is 1. Now, the reason that's important is that when we integrate, we're not guaranteed to keep the same interval of convergence, but we are guaranteed the same radius. So that's our next step here. We're actually interested in the natural logarithm of 1 minus x cubed. And we know that's the integral of this function negative 3x squared over 1 minus x cubed. And we just determined what series that is. So we'd like to integrate the series now. It's a polynomial, and we know that we can use the power rule. We're going to increase the power of x by 1 and divide by that new power. So we get negative the sum from n equals 0 to infinity of 3 over 3n plus 3 times x to the 3n plus 3. And then we add on our constant of integration. And we can divide through by 3 in the sum to simplify this a little bit. So this is our series representation for the natural logarithm of 1 minus x cubed. And we'll note that, of course, this also has radius of convergence 1. We're guaranteed that. So it does converge for x between negative 1 and 1, but we will have to check the endpoints. We don't know what happens there because, unfortunately, when we integrate, we're only guaranteed the same radius, not the same interval. Before we actually check those endpoints, though, there's one more thing that we'd like to determine, which is what's c? We currently have a power series representation, but we don't actually fully know what it is because it's this infinite sum plus a constant, and we don't know that constant. So we'd like to determine that first. We'll note that if x equals 0, the sum is actually going to be 0. And x equals 0 is in the middle of our interval. So that's a nice value to use to try and determine the constant. So when x equals 0, we're looking for natural log of 1 minus x cubed, which is just the natural log of 1. and we know the natural logarithm of 1 is 0. And the power series representation, we said the sum disappears to 0, so we're just left with the constant. So if the natural logarithm of 1 is equal to c and equal to 0, then that means c is equal to 0. So our series representation is now just the sum from n equals 0 to infinity of negative x to the power 3n plus 3 over n plus 1. Now all that's left is to check the endpoints. So if x equals 1, we'll substitute in x equals 1 into the sum. We get negative 1 over n plus 1. So we can look at the series, the sum of 1 over n plus 1. This is just the negative of that. And we can use the limit comparison test with the series 1 over n, and that will tell us that it diverges. It has the same behavior as the harmonic series. Now, the other endpoint is x equals negative 1. So we substitute that in, and we get negative 1 to the power 3n plus 4 divided by n plus 1. Now, if you take negative 1 to the power 3n plus 4, that's the same as negative 1 to the power n. So this is an alternating series. We look at the limit of 1 over n plus 1, and that tells us that since it goes to 0, we get convergence. So we use the alternating series test there. So it turns out it diverges at the endpoint x equals 1, and it converges at the endpoint x equals negative 1. So we've got our series representation, and we've now shown that it converges for x in the interval negative 1 to 1, where negative 1 is included and 1 is not. So that's the behavior we're looking for. As long as we're looking on that interval, we expect convergence of this sum, which means if we ever come across the natural log of 1 minus x cubed, and we're on this interval, then we could use this sum instead to represent the same function. Now, just to give you an idea of what it looks like, this is the original function, the natural log of 1 minus x cubed. If we look at just the first term of the series, we get this curve here. You can see it looks pretty good close to 0, but as you get out to around a half, it's starting to look a little bit different from the actual function. So let's add a second term in. This changes shape a bit, but it looks like it stays closer to the actual curve for a bit longer. We can then add a third term, and this looks similar to the first one, but it stays closer for longer. And then if we add a fourth term, it looks like the second one, but again, it's more accurate for a larger portion of that interval. So if you keep doing this, eventually you'll get closer and closer and closer to the correct curve, as long as you're looking at just that interval between negative 1 and 1. It's going to be a bit slower to converge at negative 1, but it does actually tend towards the correct value. Of course, once we go below negative 1, you can see that we're alternating between it being above the function and it being below, and so that's certainly diverging there. But on this particular interval, it's a very good match, even just at 4 terms. And we could, of course, use a whole lot more to get closer and closer to the actual function. So I'll leave you with an exercise to find the power series representation for the natural log of 2 plus x, and to look at when it converges. If you have any questions about it, feel free to come and see me in my office hours or to ask questions on Piazza. I will put the answer to the question on the lecture-specific materials page for 9105. Thank you.